Welcome to the third session in the second module, and where we continue from the second session in which we identified that an amplitude change in a sine wave is very simply described by a multiplying factor. However, we said a phase change is a little more troublesome. Let us see what happens when we change the phase of a sine wave. Let us assume that we begin with a sine wave described by A cos omega t as usual plus phi. In fact, here we have an original phase of phi 1. So, I write phi 1 here, and the changed phase is phi 2. So, I have A cos omega t plus phi 2 after changing the phase. Now, the changed waveform divided by the original waveform is not a constant independent of time, unlike the change of amplitude. So, when we change the phase, there is a problem. It is not so easy to describe. Let us take a physical example where this becomes necessary. Let us take a simple inductor across which we know the current to be sinusoidal, and let us find out the voltage. Let the inductor have value L in Henries. Let the current in the inductor be IT or ILT, if you please, and let the voltage across the inductor be VLT, whereupon VLT is L dilt dt. Let ILT be sinusoidal, whereupon VLT is going to be equal to minus LIO omega sine omega t plus phi naught. Now, of course, you can see that there is essentially a 90 degrees phase difference between the voltage and the current. We know this for a sinusoid. If you have a sinusoidal excitation in an inductor, there is a 90 degrees difference between the voltage and the current. The same can be worked out for a capacitance. But unfortunately, VLT by ILT is not a constant independent of time, and that is where the problem is. So, if you talk about sinusoids as they are, you can't quite think of the inductor like you think of a resistor, where there is a proportional relation between voltage and current. On the other hand, let us adopt a slightly different paradigm or view of a sinusoid. So, let us go back to the original sinusoid that we had. The original sinusoid that we had, the current sinusoid, was I0 cos omega t plus phi 0. And we could think of this as a combination of two rotating complex numbers. So, visualize this to be the complex plane here, and let us draw two rotating complex numbers in this plane. Let one begin at time t0 with an angle of phi 0. Let it have a magnitude of I0 by 2, and let the other begin with the same magnitude I0 by 2, but the opposite angle of starting. So, phi 0 minus phi 0 are angles of start, and let them both rotate with an angular velocity of capital omega. The only thing is, this rotates with a counterclockwise angular velocity, and this one rotates with a clockwise velocity, which you might call minus omega if you like. Now, let us describe these complex numbers. Now, let us recall how we describe a complex number. A complex number can be described either in what is called its rectangular form, where we say real part plus j times the imaginary part. In fact, this quantity j is the square root of minus 1. So, it is the primordial complex number, if you might. And what we are writing here is in what is called the polar form. We are writing a polar form. And remember, this complex number is a function of time. So, you see this omega t plus phi 0 is the instantaneous angle. Similarly, the clockwise complex number would be essentially the same as the anti-clockwise or the counterclockwise complex number, but with a negative sign for the angle. Simple. Now, when we add these two complex numbers, notice that they are complex conjugates. And lo and behold, so when you add these two rotating complex numbers, it gives you back the original sinusoid, all on the real axis. So, essentially you could think of a sinusoid as a combination of two rotating complex numbers, rotating in opposite directions with the same magnitude and opposite starting angles. Now, why is this? You see, it looks like we are doing something silly. We had nice real functions to begin with, and we are going to two complex functions. As it is, complex numbers are more difficult to deal with than real functions or real numbers, and here we have not one but two of them. Why are we doing all this? We will see in the next discussion that this is the answer to how we can make dealing with phase more convenient. Thank you.